So I'm Pedro Ferreira. I'm a professor of astrophysics here. I direct the Beecroft Institute for Particle Astrophysics and Cosmology, which focuses very much on theoretical cosmology and its interface with observations. And I'm here with Jerome Martin, who is one of the world experts on inflation. And one of the great things that you've done over the last years is build up an Encyclopedia inflationaris. Can you tell us a little bit about that?
Yes, so we all want to know whether inflation occurred in the early universe, but inflation has become so popular that we have in fact hundreds of different realizations of inflation, hundreds of different scenarios of inflation, and of course we would like to know what's the correct scenario of inflation among this plethora of possibilities. And so what we have done is that we have studied in details all these models. We have derived their predictions, and we have designed statistical methods to answer a simple question, namely what is the best model of inflation given the data that we have. And the data, of course, the CMB data, as measured by the European Planck satellite.
Mm-hmm. So this is a conversation about inflation. Very briefly, what is inflation to you?
So inflation is a phase of accelerated expansion that took place in the early universe. And well, we postulate this phase of evolution in the early universe because it allows us to solve or to explain some puzzles of the standard model of cosmology, the hot Big Bang phase. So it's not that the hot Big Bang phase is in contradiction with some observation. It's not. It's on the contrary. It's a very good model. It explains a lot of things. But for this model to work properly and to work naturally, without inflation, we have to assume things that are not very, I don't know how to say, that are not very natural, that we don't like very much. And inflation is precisely something that can make these unnatural things natural.
Can you give me an example of one of those problems?
So, well, one typical example is the flatness problem. So the fact that the universe seems to be flat. And in the framework of the standard model of cosmology, if you want the universe to be flat, you have to fine-tune the initial conditions to an amount which is hard to believe, while inflation will, on the contrary, produce a flat universe almost automatically. So in some sense, inflation is like a theoretical machinery that puts the standard model of cosmology on the good tracks, and therefore this is why it's so popular nowadays. Another example is the horizon problem. The fact that when we look at the cosmic microwave background radiation, we see that it is almost isotropic, namely the temperature that we observe is almost the same on all the direction over the celestial sphere. It's 2.7 Kelvin. In the framework of the standard model of cosmology, it's very hard to understand this fact. Of course, you can postulate that this was the case at the beginning of the universe, but it seems to be very unnatural. While inflation is a way to explain this fact and is a way to produce this observation for arbitrary initial conditions. So this is the great advantage of inflation.
So your description of inflation is very much as a particular type of dynamics of the universe, accelerated expansion, but really what you focus on are particular models. You've focused on particular models of inflation. How do you realize inflation in the universe?
Yes, so inflation is a phase of accelerated expansion, and a priori it looks a bit weird because gravity is an attractive force. So if you launch something in the air, it will gradually speed down because of the gravitational field of Earth. While inflation is like is like the opposite. You just throw away a stone and it accelerates and it disappears in space. So a priori it looks strange, but in fact, in the framework of general relativity, which is our most efficient theory to describe the gravitational field, it can be done, but there is a price to pay, and the price to pay is that the matter which is responsible for this gravitational field has to have a negative pressure. So with negative pressure in the context of general relativity, you can produce a phase of accelerated expansion. And the beauty of inflation is that since it takes place in the early universe, we believe that the correct way to describe matter in the early universe is field theory. I mean, usual statistical physics or hydrodynamics is clearly not the correct framework to describe matter at those very high energies. And it turns out that the simplest model of field theory, namely a scalar field, can have a negative pressure. So this is why we believe that there was a scalar field in the early universe that we call the inflaton field, and we believe that this field is responsible for this phase of accelerated expansion. And in fact, to have a negative pressure, this field has to move very slowly. So this means that it has to roll down its potential, and the potential has to be flat because the field has to move very slowly. And if this condition is true, then the effective pressure of the system is negative, and then we have a phase of inflation.
So now you've your description of inflation is reduced now to a theory of a scalar field in the early universe, and one can start looking at specifics. And what I liked about your Encyclopedia Inflationaris is that you when you say that you catalogued hundreds of theories, you're basically, it's pretty straightforward in the sense that you're looking at different scalar field models. Now, one of the things that really intrigues me, and when I first learned about inflation, we were brought up to learn or to see it as very fine-tuned, is how do you include the fine-tunedness of your of each particular model in your in your encyclopedia? How do you know which ones are more fine-tuned, which ones are less fine-tuned? I mean, a particular example is you say that it needs to roll very slowly, or you need a very flat potential. These are stringent constraints. There are stringent demands. How do you include that in your classification of your theories?
So I think in this Bayesian approach, the honest answer is that you don't include that. You take the model as it is,
right,
and then you study its predictions. But there is no measure of of whether the model is natural from a high energy point of view or not, for instance. In some sense, the Bayesian framework is also a way to assess what's the fine-tunings of the model, but it's a different fine-tuning in the sense that if you are given a model of inflation and some data set, for instance, the Planck data, you can derive the prediction of those models, and you will get different predictions for different values of the parameter that characterize the models. Now the question is whether you need to tune this parameter in order to fit the data or not. And from a Bayesian point of view, if you need to fine-tune the parameter in order for the prediction to be within the contours that you derive or that you infer from the data, then this is fine-tuning. And then in the Bayesian approach, you are penalized for that. But this is a different issue. This is not the issue of whether the model that you consider is natural from some high energy physics consideration. In some sense, the Bayesian approach is blind to this type of considerations.
Can you tell me just a little bit more about the philosophy of the Bayesian approach,
yes,
which is essential to your work?
Yeah. So, well, as you know, there are two main approaches in statistics, the frequentist approach and the Bayesian approach. The frequentist approach, basically, it tells us that we should find the best fit, and the model which has the best fit is the best model. The Bayesian approach is slightly different because it's also sensitive to the volume occupied by the best fit in the parameter space. So in other words, it's not only the best fit that is important, it's also the fine-tuning of the parameters that you need in order to obtain the best fit, which is important. So if you imagine a parameter space and some contour, and if the predictions of the model are totally spread over the parameter space, but the contour are only a tiny fraction of that, it's clear that you need to choose specific values for the parameter of the model in order to reproduce the data. And from a frequentist point of view, this would be perfect because there is a specific values of the parameter such that you fit the data. From a Bayesian point of view, this would be very bad because only a tiny fraction of the possible values of the parameter leads to a good fit.
So in some sense, the model would be unpredictable.
Yeah, so the Bayesian approach, if you wish, it favors the best compromise between simplicity of the model or no fine-tuning in the model and quality of the fit or ability for the model to reproduce the data. It's a compromise between these two things. While the frequentist approach is only sensitive to the best fit, so to your ability to find specific values of the parameters such that you reproduce the data.
So going back to what I asked, presumably you could include more information about different levels of fine-tunedness in your analysis. In the sense that, for each theory, for each theory you have, you say, well, these parameters can really only vary between these values for them to be consistent with, high energy physics. And then that would be factored into this, as you say, the range of parameters that you're allowed.
So this is the question of the priors,
yes.
I believe, yes. So you have two types of priors. You have the priors on the parameters given a model. So usually they come with the model. For instance, imagine that you have a model of inflation which is given by a constant plus a small correction that you obtain from quantum field theory, a one-loop calculation. We know that the amplitude of this small correction is controlled by a parameter that has to be small. So if the parameter is small, then we know which type of prior in a Bayesian analysis we should require or we should impose. So usually, when you know the model, and this, by the way, this is why it's very important before performing any Bayesian analysis to really understand the physics behind the models of inflation, because this is exactly the physics behind the model that gives you the prior that you should choose in your Bayesian analysis. So this part, I believe, is well under control. Of course, you have also a prior on the model itself. And this is much more difficult. And usually what is done is to take the same prior for all the models. But if you have some a priori and you believe that one model is much better than the other from some other considerations, maybe you could consider modifying the priors of the model themselves. So in the sense, what we are really establishing with this Bayesian analysis is not the probability of a model, it's really the ratio of the probability to the prior of the model. Then you are free to choose the prior that you wish for the model.
So often people don't talk about inflation as a theory, but as a paradigm. And I think you have said very clearly that, when in your work on the Encyclopedia, it's about these hundreds of models, and you can think of them as hundreds of theories to some extent. You've also said something very intriguing about what is a good theory and what is not a good theory, where you said that from the Bayesian point of view, if your range of parameters, if you're allowed, is so large, and that your data pins you down to be one value, that's not very good, because you have to fine-tune your parameters. Now, to be the devil's advocate, to be a little bit controversial, often you put up these plots where you have some axes, right, and you have all these various models, okay, but the data really pins you down. You know, the good models are only in this small area, which you call the good evidence. But there are all these other models spread out around. Wouldn't this mean that inflation as a paradigm is not great because it gives you so general predictions that you can basically get anything, and so you really have to pick only one, only one of them. You're fine-tuned to one particular theory. Why can't one apply this kind of reasoning to that?
Well, I think what is important is also to look at the scales on this plot.
Yes.
Because we have the impression that everything is spread in this space, but there is also the question of the scales on the axis.
Yes.
So one of these axes is the spectral index.
What's the spectral index?
So the spectral index is a quantity that characterizes the power spectrums of the fluctuations. So the power spectrum of the fluctuation is a quantity that tells you the amount of signal that you have at a given wavelength. And there is a particular example of, and very well-known one of power spectrum, which is the so-called Harrison-Zeldovich power spectrum, which was known much before the advent of inflation. And the Harrison-Zeldovich power spectrum is also known as a scale-invariant power spectrum. And it's a power spectrum which is flat, so which means that we have the same amount of signal at small wavelengths than we have at large wavelengths. And the predictions of inflation is that the power spectrum of the inflationary fluctuation should be close to scale invariant, but not exactly scale invariant. And I emphasize that this was a predictions of inflation in the sense that it was made before the measurement of the spectral tilt by the Planck satellite. And so yes, so the predictions of inflation is that this spectral tilt. In the usual language, the Harrison-Zeldovich power spectrum corresponds to this spectral tilt equals to 1. So the spectral tilt is 1. NS is 1 for an exact flat power spectrum. And what has been measured by the Planck satellite is that NS is 0.96, which is indeed close to 1, but not exactly 1. So I believe this is a beautiful confirmation of a prediction made by inflation. And to answer your question about the spread of the data, so I come back to your point that that it seems a priori at first sight that all the models corresponds to different region in this parameter space, but I repeat that one has to look at the scale, and the scale in this plot, so the horizontal axis is the spectral index, and in fact the range of variation on this plot is quite small. It's always NS close to 1. So I would answer that inflation cannot predict anything for the spectral index. It has to predict that NS is close to 1. It's true that we don't know how to predict what's the value of NS. I mean, if we are given a model of inflation, we can say what NS is. But if we don't know the model of inflation, if we don't know to which realization of inflation we have to deal with, we cannot say precisely what NS is, but we can say that NS is close to 1. And in addition, there are models that predict NS which is very far from 1. For instance, there are some bouncing models that predicts NS equals to 3. And 3 in this plot, in fact, a value of 3 in this plot would be completely outside the plot. So, yeah.
It's interesting. So there are two follow-up questions before we end this part of the discussion. One is, you say that inflation predicts that NS isn't exactly 1. But from what I recall, inflation doesn't predict that NS isn't exactly 1, but it can be greater than 1 or less than 1. Right? So all it does is it predicts that it's somewhere around there.
Absolutely. Yeah.
Okay, that's the first thing. The second thing is, I want to go back to what you said. You said something very specific when we were talking about Bayesian. Bayesian gives you a good idea of whether a theory is good or not. And the only thing you said was, your theory predicts a range of parameters, is allowed by a range of parameters. And if your data lies in a small patch of that range of parameters, then that theory isn't that great. Okay, so the fact that you say that NS is close to 1 is fine, but that's not a quantitative statement, really, right? The quantitative statement is the data lies in your contour, lies on your parameter space and is quite tight, and the allowed range is much larger. And so I go back and I think, using your language, it does mean that, okay, inflation is close to 1, but it's not close enough to 1. The range of parameters is still sufficiently large that the data pins down, is very small, only pins down a very small subset. So, it is fine-tuned, using your language.
I would say it depends on the model.
Well, the thing is, your whole premise is inflation is this range of models, right? So you've got all these models, and so there are this range of models. So even though they mostly predict close to 1, the spread is sufficiently large compared to the data that you can pretty much get anything.
I agree that you can get pretty much everything around 1 if you don't specify the models of inflation.
Yeah.
But I also think that I have never computed something that would be the Bayesian evidence of inflation because I don't know how to do it.
Right.
So the only thing I have done is to compute the Bayesian evidence of various precise, accurately defined models of inflation, which is different from computing the Bayesian evidence of inflation as a paradigm.
Can you very quickly just explain what you mean by Bayesian evidence?
So Bayesian evidence is a quantity that describes the ability of a model to fit the data and the ability of the model to fit the data without fine-tuning, I would say. So in other words, a good model of inflation is, according to the Bayesian evidence approach or the Bayesian approach, is a model which can fit well the data but without wasted parameter space. So this means that if you have a contour that you infer from the data, and if you have a model with some prior for the parameters, if when you change the values of the parameters, the prediction all lie within the contour, this model will have a very good Bayesian evidence. But on the other hand, if you have a model where when you vary the value of the parameters, some points are inside the contour, but some others are outside the contours, then you will get penalized by this so-called wasted parameter space, and the Bayesian evidence would be bad. So really, the Bayesian approach is something which tells you about the best compromise between your ability to fit the data, so to find a point right in the middle of the contours, and the simplicity of the model, in the sense that all the values of the parameter should predict something which is compatible with the data.
Very good. Okay, I think that's very clear.